Good morning, afternoon, or evening, physics students. This is the final unit in Physics 30. We're looking at modern physics. This will be day one, and we're going to get at looking at particle physics first. So we start with particle physics. We look at a little bit of quantum physics as well. Those are the two main areas that we're going to be looking at in terms of physics here. Particle physics, a little easier to understand, uses E equals mc squared is probably, there's some chemistry involved and there's some nuclear decay. We talk about things within atoms. So it's particle physics that we're going to look at first. Then we roll into doing a little bit of quantum theory, and that talks about quantum theory, electromagnetic radiations in there. There's also quantized theory of light and things like that, and time dilation and things like that. So we'll do probably about 10-day type unit, maybe not even, but around there. It's a short unit, a couple weeks long. We're starting here at the end of May, so we'll be done in early June, which will be good because it'll give other people that are behind, time to catch up and get things done and in and things like that. And also we can do a little bit of studying for the final exam. This unit, I will probably just have a hand in. So it's very important that you do the hand in and get it in. I probably won't have a quiz for it. I'll just add a few extra modern physics types questions on the final exam so that we don't have to do an exam and then a week or so later do the final exam right after that. So let's go through what we're going to look at today. This is day one, unit 4 in physics, and this is the modern physics unit. Okay, and what we're going to look at today in modern physics is we're going to look at particle physics. The first couple of things we're going to look at under particle physics are we're going to look at the notation, isotopes, notation, and we're going to look at some basic forms of radiation. And basically the nucleus of atoms. Okay, so that's what we have, okay, for today. Those four areas, we'll kind of look at it in terms of going through a couple of things for review, first of all. So the first thing is from chemistry, we know just in terms of the basic particles of nuclear decay in modern physics. Okay, let me just set up so in chemistry, we know that all atoms are made up of protons and neutrons and electrons. Okay? Oops. At least in that theory. And these are all the atomic particles that we're going to deal with. We're going to look at some radiations. Okay, we know that the neutrons are neutral. The protons are positive. And electrons are negative. So we know basically from chemistry, those particles, hopefully, if you haven't taken it, we'll be reviewing it here fairly thoroughly, so it's not a big deal. The other thing that we know as well is that we know the electrical uh, laws of electric charge, right? Opposites attract, like charges repel. So that gives us something quite an anomaly. Okay, there's an anomaly in the world of atomic physics now, based on the theory that, well, we have a nucleus. Okay, if we have a nucleus, let me just fix this up a little better here. It's too fat. Okay, now in our nucleus we have some protons, and we'll throw in a few neutrons there. The theory is okay, we have this nucleus here, and what happens is when we've got some electrons floating around it, so we're orbiting around it depending on what quantum theory. So then we got our electrons. So it makes sense to us that the electrons, I hate this fat pen, are held in place or are attracted to the protons in the nucleus. Okay, by electromagnetic force. Or, well, we'll just call it electric force because it's not magnetic, right? I just get used to saying electromagnetic last unit. Are attracted okay, what am I saying? I did that already. Are by confusing myself. That's so bad. By electrostatic force. Okay, so that's what's holding them in place when they're around the nucleus. Now, the thing that you should know that is an electron cloud is much, much larger than the nucleus. Okay, so the nucleus, on average, the nucleus would be 1,000 or 10,000 times. Yeah, no, 10,000 for 10,000 times smaller in diameter than the electron cloud. So there's a little nucleus and then a bunch of space. So if you're in the room there, average classroom, and the electron cloud was the area around it or the walls, the nucleus would be like a little dot in the middle of the room, kind of idea. Okay, 10,000 times smaller box than the room is. Okay, so there's a lot of space in atoms, and that the electrons are held there by electromagnetic forces. However, how come the protons, which electrostatic rules tell us should repel each other, how come they don't fly apart? What's going on? Well, there's a force that they call the strong force. That's what they use it. That holds protons together. So in a nucleus, an atom, protons with more than one proton. Strong forces exist. talking about named strong forces, are present that overtake or overcome the repulsion of the protons, to hold the protons together. Okay, so, and a lot of weird things happen in particle space. So, firstly, this strong forces, what they do and what they say is they're about 100 times stronger than the electromagnetic or the electrostatic force of repulsion. So, and these strong forces only come into play when the two protons get really close together. Okay, when they come within about a diameter of another proton within each other, these strong forces come into play. So they're literally called the strong force. My book here, I don't know if you guys use a book, but in most books, they'll call them strong nuclear force. Okay? So some books oh, I can't. Oh boy. Strong nuclear. Type and hold the. I'm gonna have to put. I can't type and hold the shift key at the same time. So let's put the cap locks on. Let's see if I can. What are they? Nuclear. I'm gonna have to look this one up. This is my spelling. I want to make sure. E-A-R. There we go. After 400 attempts, I got. Some call them strong nuclear forces. Some call them strong forces. Others will call them or nuclear forces for short, in short. Okay, so strong nuclear forces, the strong force or nuclear forces, they all kind of use them interchangeably, depending on what book you have. Okay, and they come into play when the protons are close together inside the nucleus. Okay, and they're about 100 times stronger than the electrostatic force of the repulsion of those protons. So they're still held together. At least that's the theory, anyway. Okay, they don't have 100% evidence for that yet, but that's in theory. Okay. Okay, so we've got this nucleus, we've got these electrons. So we have a way of noting this. So we're going to talk about the isotope notation. So when we talk about isotopes, maybe I'll just keep it in. Let's see if I can spell isotope right. Better look that one up because my spelling sucks today. Okay, so isotopes, when we're talking about isotopes, we're basically saying that they contain protons, neutrons, and electrons in them. And isotopes of different atoms can have different nuclear masses. So these are different Don't want to do capitalize now. Configurations of atoms, basically of atoms. So we have a particular way of looking at it. So if we say that X is the chemical symbol, like this, and out here we'll put something, out here we'll put something, and in here we'll put something. Okay, if we do the isotope is written like that, this represents the charge of the particle. Okay, or isotope. This will represent the number of neutrons and protons in the nucleus, or nuclear mass. Okay, atomic number. Oops, I got to put an E in there, sorry. EU. Okay, and this is the number of protons. Okay, so we have a couple of different numbers. This is the atomic mass unit. This is the is basically, so hydrogen would be 1, helium would be 2, and so forth. Okay. Okay. Little note on the side. Charge is formed by having missing or extra electrons. Okay, so missing or extra electrons are forming the charge. Otherwise, if you have a completely neutral atom, protons and electrons will be the same. Okay. If you have an ion, you're going to have missing electrons if it's positively charged, and extra electrons if it's negatively charged. Okay. Okay, so this is usually called atomic number. And this is usually called atomic mass. Okay, but number of protons, atomic mass, number of protons and neutrons together, atomic number. Okay, so an example of this, if you don't have a periodic table handy, it might be a good idea for you to dig up a periodic table. Okay, I've got one in the back that's why I got my little physics book here. I got one here that I'm going to use because it'll help us give us the atomic numbers of certain elements. So for example, if I had neon, which is element 10, so if I had, well, let's do potassium because I know potassium is radioactive. So where's potassium? It's 19, I think. Yes. Okay, so if we had potassium, so example, say we had a potassium ion here, 19, and this was, let's say, 30. Okay, this would mean I could ask a couple of questions here. Let's type it out so it's clearer. Okay, how many electrons? Well, let's go how many protons? Electrons and neutrons are there. Okay, so protons are always the bottom number. Protons equals 19. Okay, it's always a number. The top number is the protons plus the neutrons. So protons plus neutrons equals the atomic number. So in our case, the protons are 19 plus the neutrons is going to equal 30. So that means N equals 11. So there's 11 neutrons. Okay. Pretty easy to do. So the charge, okay, the number of electrons is going to be equal to the number of protons minus or plus the charge, right? Okay, so obviously electrons, if you have extra electrons, you have a negative charge. So number of electrons, okay, we should have 19 in a neutral one, but we have, because we have plus one, minus one missing electron, for the plus one charge. Okay, so in this case, we have 18 electrons. Okay, it's going to be the same number as the protons in a normal neutral atom, but this is not neutral. It's charged plus one. Okay, let's try another one. Same question. Let's say I had, this is my periodic table here again. Let's say I had chlorine, okay, no charge. Chlorine is element number 17. 36. Yep. Find the protons, neutrons, and electrons. Okay, so obviously protons equals 17. Neutrons, it's going to equal 36 minus 17. Okay, this number minus this number. So if we do the subtraction on that, this would be, what would that be? 19. So we have 19 neutrons. And then no charge, so that the electrons, which are usually that, are going to be the same as the protons if there's no charge. So there should be 17 electrons. Okay, so that's the basic chemistry isotope notation, okay, and how it's used. Okay, so not too difficult to use. Potassium, the symbol goes here. I guess I should have put, I don't know if I did that. Look back here. This X, we should say, is a chemical symbol. I didn't label it in here, did I? See that? This is the chemical symbol. Of the element or particle. Sorry, guys. My mistake there. Okay, so that's basically how it works for that. Okay, the next thing we got to look at, if we're comfortable with that, is we got to look at what kind of particles we're going to be talking about in terms of radiation. So what radiation is, or what happened back in the late 1800s and so forth and around there, is physicists and scientists are figuring out and working on atomic theory and theory of the atom and all that kind of stuff. And what happened? One of the first guys was Rutherford. And Rutherford, he was, worked in actually McGill University in Montreal for a while until he moved back to England because he's an English guy. He was basically shooting some radiated particles called alpha particles, which we'll talk about in a minute, at gold foil, and they didn't know that the atom had a nucleus. And what happened was this gold foil, he would expect these particles to fly right through it because they were so highly charged energy. But what happened was some of them were deflecting, and he was wondering, why are these things deflecting? And what he figured out was they were deflecting because they were either hitting the nucleus and bouncing backwards, or they were coming close to the nucleus and getting deflected by the electric charge of the nucleus. And then they decided, well, all atoms have a nucleus in them, and this is how they discovered different particles in there, things like that. So for us, what Rutherford did next was he took basically a source of radiation, because he was working with radiation, and he shot this through a magnetic field, and he found that in the basis of this, there was 3 kinds of deflection in there. And these are the 3 base kinds of, there's radiation that we will talk about in physics here. Okay, so types of radiation that we see. Okay, that's what we're going to look at. So the next little topic here is 3 radiation. Okay, there are more than this now in theory, but we're going to just look at the basic 3 in radioactive decay. Okay, so when something decays radioactively, it releases particles. Okay, the first type of decay that we see is called an alpha particle decay. So we've got the alpha particle. So when a bigger atom gives off an alpha particle, what it's actually giving off is alpha particle symbols are usually written like this. Oops, not like that. Like the Greek letter alpha, the little one. Okay, so like this. And an alpha particle has 4 nucleotons, or nuclear particles, and 2 of them are protons. Or, as we know that's helium, because helium is the second element, it can be written like this. Okay. Now, this is a positively charged particle. Okay. So this thing has no electrons hanging around it. So, okay, now what happens though is they often do not write this. Okay. They often take this out and write it like this. We know that this is positive charge, even though the charge isn't written there. It's just because the physicist is being lazy. Everybody knows these are positive charge. Everybody knows they don't have any electrons because they're nucleotons. There's no electrons with these. Okay, so this is the first particle. This is a nucleoton. It's 2 protons and 2 neutrons stuck together, written like this. Okay, it's positively charged. And it's radioactive and very dangerous. It's really heavy. It's got 4 particles to it. 2 protons and 2 neutrons. 4 total nucleotons. Okay, it's positively charged, and this is the first type of nuclear decay. Okay. The other type of decay that he discovered was a negative decay, which was an electron decay. Okay, where do the electrons go? Well, they have to decay too. So he called this beta decay. So there's also beta decay, or the beta particle. Okay, and this is a particle that is just an electron. Okay, so it has no protons and no neutrons. So no numbers here. In fact, it's usually written with a negative on it. Okay, so beta decay looks like this. So the symbol for beta is kind of fancy B. Okay, and it has no protons in there and no nucleotons or anything like that, but it can change into or take away one of your protons. So it's like this. It's usually written like this. Okay, so it's kind of a released negative. So like that, or it's basically an electron being released. So it's sometimes written like this. Okay, and you've heard the word positron before. Positrons are beta decays that are negatively charged. It's one emitted electron. Okay, it's one emitted electron in radioactive decay. Okay, this is one positively charged helium nucleus. Okay, 2 protons and 2 neutrons. Okay, and the last one, C, is gamma radiation. Now, gamma radiation is the emission of nuclear energy in the form of a ray. It's not particleized, okay? It's electron transfers energy levels in the atom. So it shifts from one level in the atom to another level in the atom, and it emits some energy called this gamma radiation, okay? So the other one that he discovered was gamma radiation. See, gamma radiation. Gamma, we can't call it gamma particles because it's not a particle. We'll call it gamma rays. Okay, these are emitted energies when electrons change levels in the atom. Okay, so they're kind of going from orbital 1 to orbital 2 or something like that. It has no mass. It's neutral. Okay. What do they look like? They're just written like with the Greek letter gamma here. Let me just fix this emitted here. There we go. Okay. So let me just get my preview up here. I haven't turned that on yet. Sorry, guys. So I can kind of keep track of the time here. Okay. Oh, 34. So we're going to have to wrap it up here in a quick minute or two. Let me pause quickly and look up the Greek gamma symbol because I can't remember it right now. Okay. So I kind of looked it up there. Gamma radiation symbol looks like this. Okay. If I go into here, let's go back to here. Use the same set. Okay, so that's beta. So gamma kind of looks, depending on if they give it a capital letter or a little letter, kind of looks like this. symbol here. Let's see. Like that. Okay, similar to this one, but laid over, no mass to it. Okay, no charge to it, so nothing around it. Just gamma radiation. Sometimes it's written in the capital letter form, which is kind of like this. Kind of without the loop, just a capital letter. Okay, gamma radiation. Now we focus a lot on beta decay and alpha decay because those are the basic energy decays in radiation. Okay, let's take a look at what our outline was today. So we've gotten the particle physics part. We've looked at this. We've looked at the basic forms of notation and the nucleus of an atom. We basically talked about strong force or the nuclear force that holds it together. Okay, so we'll kind of stop here today because we're getting into 35 minutes. The one thing I do want to, I should put this down, but we should get down the particle masses because we're going to need those for next day. So we have some constants that we need. So let's just do those before we stop today. So some particle constants. For mass. So let's do a proton. Okay, what the mass of that is, and I'm going to do it in the marker, equals whatever, and then we'll do a neutron. And we're going to need this because we're going to be calculating mass defect and nuclear binding energy next. And we also need a electron. Okay, the three nuclear particles. What are the masses of each of these? So, sorry guys. Significant figure-wise. Okay, so let me pause again and dig them up to, let's say, 2 significant figures. Okay, so I was doing a little bit. We're going to have to go more than a few significant figures. We're going to have to go down to about 4 or 5. So a proton is 1.6726 times 10 to the negative 27 kilograms in mass. A neutron is slightly heavier, so let me just get that one here. Okay, so a neutron, let's see here. There it is. 1.67. Sorry, guys. 1.67, and it's slightly heavier. It's 1.6749 times 10 to the negative 27 kilograms. Okay, and then electrons are significantly lighter. So we'll put those up, and then we'll call it a day. And we'll look at some equations here. Okay, so let's do an electron here. Mass of a neutron, mass of a proton, mass of an electron. Okay, so mass of an electron is 9.109 times 10 to the negative 31. So this one's significantly smaller. Okay, just making sure here. 9.1 times 10 to the negative 30. 9.109. So it's 9.109. Making sure we'll go down to enough significant figures here. Yep, times 10 to the negative 31. Okay, and we're going to need that for our next little bit that we're going to do on mass defect, nuclear decay. We're going to actually look at some actual decay series here, and that's what we'll do next day. But that's probably as far as we should go today, as we're already into 40 minutes. So we'll do that next day.